Okay, sorry for the technical problems, but now I assume that you are able to see my screen. Here we have a small agenda of my presentation. First, I will start with a very short introduction of my person and the company I'm working for, SimPlan. And the second part of my presentation is a description of the phases we follow in our supply chain design projects with anyLogistix. And the third part is focusing on a project example we did some time ago in the building material industry with anyLogistix. So let's start. Yeah, my name is Till Fechteler. I'm working for SimPlan since 1997, so now more than 25 years. As you see, I'm also working in the area of supply chain optimization and simulation since 2012, and also working on intralogistic projects like distribution centers in the FMCG sector and spare part centers, for example, in the automotive industry. I'm head of the SimPlan office located in Braunschweig, and Braunschweig is focused on supply chain optimization and simulation. SimPlan has been founded in 1992. Currently, we have more than 120 employees. Most of them are consultants. We have 12 sites in Germany, and in total in our group, we make a turnover of nearly 17 million euro. The market share is shown below here. 50% is in the automotive industry, 40% intralogistics, and 10% is completely broadly distributed all over any kind of industry or industry area. SimPlan is focused on material flow simulation in production and logistics, and we also sell the software we are working with. Here in brackets you see the most prominent examples: anyLogic, anyLogistix from the anyLogic company, plant simulation from Siemens, and Emulate 3D. Okay, let's go on. I mentioned that or Ryan mentioned that I will show you our experiences in supply chain design projects, and usually we follow the phases you see here on the screen. So first we start with a process analysis, then we have the data analysis and data transformation, and then we go into anyLogistix and doing greenfield analysis or network optimization, mainly to solve location problems, and or to do simulation if we need to get an understanding of the processes within the supply chain. In case of data analysis and transformation, we mainly use Python to work with the data. And on the evaluation side, we are using mainly Tableau, Power BI, or Excel. I will go into detail in the following slides regarding the processes. And yeah, let's start with a process analysis and the requirements we have in our project. Usually, the main target of our projects is to find a more cost-effective network variant, or to prepare the network for the future, for the time within 10 or 15 years. And 90% of all our projects are about location problems. So we are doing a greenfield analysis or a network optimization. The minor part of our project is using the material flow simulation component of anyLogistix. So this is very important. And here on the lower part of the slide, you see the typical requirements we are getting from our customers. So, for example, the number of hubs is limited to a given number. We need a maximum distance from the DCs to our customers, or we need a given delivery service level, or we have a delivery frequency we need to meet in our project. So there are a large number of requirements that always come up in such projects. And here you see also some very special requirements from past projects. For example, ships cannot dock during high tides in case of large rivers where you have a tank ship that need to have a specific level in the river to dock and to unload. So very special requirements. Then we have the data analysis and data transformation phase. As you may remember from the diagram I initially showed, we need input data for our projects. We need customers and their location or their addresses, warehouses, factories, suppliers, for sure products, and the demand and cost information. And if we do a simulation, we also need storage, sourcing, or distribution policies. And for sure, in case of the network optimization, we also need flows, production strategies, and storage strategies. Mostly we get the data in form of comma-separated text files. The preferred format we use, or Excel, if the customer is more familiar with Excel and is not familiar with this format. And then we take the data and do an analysis and validation of the input data. So we try to get an understanding of the data. Are we using the correct data, or need the data to be filtered? And we also do corrections if necessary. For example, in case of missing values in column. And we usually do the geocoding in that phase, because we better have this under control, and we can also do some validation of the geocodes that are determined. So, for example, if we get back from the geocoder latitude, longitude 00, then there's something going wrong. Or we can, if we have country information, we can check if the determined location is within the correct country. So these are checks we do in case of the geocoding before we go into anyLogistix. And for that, we mainly use, as already mentioned, Python. In case of analysis, we use Excel, Tableau, or Power BI. And then once we have a good data set, I need to point out that in most cases we are working with delivery data, and if we have a good data set, we start the transformation. So we need to bring the data into a format anyLogistix is able to read. It's an Excel format, or it's an Excel file that follows a given format. And often the sheer volume of data makes simplifications necessary. And for that, we are using cluster algorithms, or we are filtering the data according to given restrictions. In case of clustering, we try to find representatives for products. This can be product groups or product hierarchies. In case of customers, for sure, you are using 3-digit or 4-digit postal code areas. So aggregating customers within postal code areas. And in case of shipping types or means of transport, it's also possible to reduce the number of shipping types to a smaller number to reduce the complexity within the data set. And then we are doing the transformation into the format anyLogistix is able to read. And for that, we developed a Python library that enables us to read the data in and to simply export it in the anyLogistix format. And then we start applying the methods based on the requirements of the project. So if we have if we need to solve a location problem, we are applying a GFA analysis, a greenfield analysis, or a network optimization. And if we need results in case of the processes within the supply chain, then the material flow simulation comes into play. So if you want to evaluate stock levels if you want to evaluate the stock level you need for a given delivery service level, for example, 99%, then you need to do a simulation. Or if you have special transport relations like helicopter transports or express transports, then you need to set up a material flow simulation. Or in case of production planning, or which type of production planning need to be done in the network to enable or to ensure that you always have a product on stock. So these questions are not sufficiently answered by using an optimization model. And as previously mentioned, GFA and network optimization are only can only be utilized to solve location problems. Okay, let's go on to the project example. I already mentioned that it is a network optimization in the building material industry. We need to, or the task was to optimize the German supply network of the producer with regard to future requirements. The objectives were the question how the future German supply network should be configured, a centralized version versus a decentralized version. At which locations should which article be produced or stored, and what happens with the key figures, costs, delivery service level, delivery times, if the network is changing according to what we did in the network optimization. The procedure we follow was as described. We analyzed the data and transformed the data by using Python, and then we imported the scenarios into anyLogistix in the 2.14 version, and carried out greenfield analysis and network optimizations. Here we have some facts about the network. We have in case of products, we worked on product hierarchies. So I don't know exactly, but I think the delivery data contains more than 6,000 products. So we are focusing on the product hierarchies, and we have 1,540 customers in our network, which was a combination of 3-digit postal codes and shipping types. We have 7 shipping types identified from 20 or more than 20. We have 34 shipping points, 24 factories, and more than 580 cost rates for production, which basically was a combination of factory location and product hierarchy. And yeah, to make the model solvable in a reasonable time, we need to apply further simplifications. For example, we added a proxy customer for shipping types with fixed shipping costs, collectors, for example, and parcel service. And we further compressed the shipping types from initially 7 to 5. And we also reduced the number of relations within the model that lead to a reduction of 0.5% in case of handling weight and 3% in case of transport. So making the model less complex to ensure that we have reasonable times for solving. I can say you that the optimization sometimes run 6 hours or 7 hours to complete, and we had even situations where we didn't find a very good gap, and yeah, that's the case. If you have a complex model, then you need some time to get the optimization up and running. Here you see an overview of the data we have used. As mentioned, we have used order lines, delivery data, the customers and their addresses, shipping types, for sure products, plants, factories, with production capacities and production range, and shipping points, and as yeah, already mentioned, shipping types. It's duplicate there. Okay, and to get a complete scenario, we also need to scale the order data for a future scenario. So we have a target year 2030. And here you see the procedure we followed regarding the data scaling. So we are separated the data records by sales organization, then applied growth factors within the product hierarchies I earlier mentioned. In case of the separate sales organization, then merging the data records, the existing data records with new order data, and then create new deliveries for each customer from the new order lines. And we created the new order lines by simply duplicating existing order lines. And here you see some key facts. We increased the shipments by 57%, the number of pallets by 123%, and the total weight that is transported in the network by 120%. So with this information, we get into anyLogistix and did the optimization. I can say you that we did 50 or 60 optimizations to come up with 15 optimization runs. We are further evaluating regarding results, and this results are shown on the next slide before we go into the anyLogistix scenario. So first, the first fact is that a purely sales-oriented network structure, for example, with 5 central warehouses resulting from a greenfield analysis, is not economically regarding transportation costs. So we have higher transportation costs if we have fewer warehouses in Germany. We evaluated the separation of sales organization. Currently, the sales organizations are selling all products, and so the idea was to separate this. So each sales organization is responsible for the transport of its products, and we try to investigate what happens to cost figures, and we find that that only one sales organization has slight cost advantages, but we result with higher total costs for the complete network. So the separation of sales organizations is not useful. Then we established network alternatives. We find that two new distribution centers in west of Berlin and in the Ruhr region lead to savings regarding transportation costs of 3.3 million euro. And additionally, in this network variant, we also utilized two already existing warehouses. We tested also what happens if we supply the customers only from one CDC. Currently, the customers can be supplied from each shipping point or each factory. And we wanted to evaluate what happens if a customer is assigned to only one CDC, and we find that the transportation costs are increasing by 1.7 million euro. And a central structure with two existing warehouses and 5 CDC lead to cost savings in case of by 1.8 million euro. And we were able to reduce the number of active shipping points to 7. To give you a visual impression of the network we are talking about, I have this three evaluations done by using Tableau. We have the base scenario. Here you see the shipping points and factories, and the arrows are representing the material transport to customers. So you see that nearly every location is delivering to every customer. So, for example, locations in the northern part of Germany are delivering to customers in the very south of Germany, for example. So we tried, as mentioned, this alternative where we have 5 CDC from a GFA analysis and find that the transportation costs or the total costs increased by 3.8 million euro. But you see that the network looks more nicely. So we have a clearer structure, but we have large distances from the CDC to the customers. For that reason, the transportation costs are increasing. And in case of the third example, we have 5 CDC from the GFA plus 2 already existing warehouses. The first one is located here and the second one here. And in this case, we get this already mentioned saving of 1 million euro regarding transportation costs. So this was the variant that the customer is further evaluating to change his distribution network. So let's have a look at the model itself. So here is the anyLogistix scenario. We have the 1,540 customers, and you see here we have the 3-digit postal code and separated by a slash the shipping type. So we, as mentioned, we have a combination of postal code area and shipping type, and for sure for each customer and product combination we have demand. So in this case we have historic demand, so a demand by date. We have heavily used location groups to set up the model. So we have customer groups for all customer, for the customers belonging to a given shipping type. And we have customer groups regarding countries, and also for the the 3-digit postal codes. And in case of the transport relations or the paths, you will find again this shipping type. So we have relations from the shipping points to the customer with different transportation cost rate, and different type of cost calculation. And yeah, to finish the presentation, we have also used product groups to set up the model. And as mentioned, we have specified production restrictions, maximum throughput and production costs for the model. And yeah, the product flows are limited according to the capacity of the shipping points. So you will find where is it? Yeah, you will find here. You will find also maximum throughput for this product flows in case of the flow from a given shipping point to a customer group. This is how we set up the model. And as mentioned, the runtime changes dramatically based on the scenario we evaluated. Sometimes we are finished within 1 hour, and sometimes the optimization took 10 hours to finish, and or you run into the time limit. Thank you very much.